So, continuing with the mode locking process. So, here we had come to this time bandwidth product identity, delta nu delta t is almost equal to 1. So, about the fuzziness in the measurement of each of them, something like the uncertainty principle. So, then here just what does this formula say? That means, if my delta nu is inversely proportional to delta t. Okay. So, if my delta nu is large, then my t will become very small, the pulse duration. This will give me my pulse duration in a mode lock pulse, and delta nu also depends on the number of modes. See here delta omega, and I have converted that delta omega to delta t. So, delta nu has something to do with the number of modes. So, if the number of modes is large, your delta nu becomes large and your delta t becomes very short. Okay. So, that is the idea of getting a very short pulse from a mode locked laser. So, you have a very sharp pulse from a mode locked laser. Okay. So, this is the pulse width here, okay. And I am not talking about the the separation between two pulses, that is separate, that is 2d by c. Okay. 2d by c, the round trip time here 2d by c, distance upon time, distance upon meters per second. So, it becomes second distance. So, it is a unit of seconds. So, this is the time between two pulses, but the width of each pulse is just this much, which is given by delta nu is proportional to 1 upon delta t, or delta nu delta t is equal to 1. This will give you the width of the pulse, and this will give you the distance between two pulses. Okay. So, this distance between two pulses happens at the round trip time. That means, at the end of the round trip, all these modes are locked in phase, or they are synchronized after one round trip. They are nearly synchronized after one round trip, these n number of modes. Okay. So, that is the importance of T, capital T. So, as you see the number of modes, you increase the number of modes, you shorten the pulse. And with mode locking, people have shortened the pulse from femtosecond. Of course, they can easily get femtosecond pulses from mode lock pulses. Picoseconds also, femtoseconds definitely, people have got from lasing action there. Now, how exactly would you make this mode locking work? Okay. So, I'll go back to the saturable absorber. So, here I assume that I am using a saturable absorber as a shutter, okay, inside my resonator cavity. So, I have this resonator cavity, okay, and I have this saturable absorber. So, generally these saturable absorbers, initially they were dye molecules dissolved in a soluble liquid, okay, and they acted as saturable absorbers. But nowadays you get semiconductor saturable absorbers. Okay. So, you get something like that, and then they are much more compact and not messy like the dye. So, people have started using semiconductor saturable absorbers nowadays. Most often they use that, and dye part is okay, in very special cases perhaps dye is used. Now, as we have seen in the previous slide, the characteristic of a saturable absorber is like this. Okay, this is the absorption and this is the intensity. So, you have these two states. Now, suppose consider a dye molecule or something, and I have said at low intensities here, at low intensities the dye gets bleached. That means everything is absorbed there. Okay. So, suppose I consider two levels of a dye. So, all the molecules are sitting here, a ray of beam intensity beam comes in, and all of them, the ray gets absorbed and all these go up to this level. This is putting it in a very simplistic way, but this is the concept. Okay. Generally dyes may not be two level system, they may be some 3, 4, much more than that. If it were so simple as this curve also would have looked like this. Okay, exactly, but it's not that. It has this sort of a, this is the real curve and this is the ideal curve of a saturable absorber acting as a shutter. So, all these molecules, you have this low beam of light, all these molecules from here just go up to this higher level. So, when you have some more beam coming in, okay, at a higher intensity, this level is empty. Everything is there. This level is empty. So, all it has to do is that light has to just pass through. It does not get absorbed. That is how you have at high intensity, you have higher transmission and almost zero absorption. Okay. So, I have this light within this saturable absorber. Sorry, not within the saturable absorber, within the resonator cavity, and it should be moving up and down, this light. But what happens is, instead of moving up and down, when these intensities are low, they bleach this saturable absorber. By bleaching I mean everything goes up to this level. Okay, they bleach this saturable absorber and nothing comes out here. All of them, all that light has been absorbed here. And they help in bleaching this dye, the dye molecules. Or in case of a semiconductor, the same thing is happening. Okay, so nothing is coming here. So that means this shutter is closed. At this point, the shutter is closed. Then I have another intensity, or maybe part of the same beam, another intensity coming in almost immediately at this time, and it passes through the shutter and it comes to this rare mirror. Okay. So, all these this ray of light has passed through, has been transmitted through this shutter, through this saturable absorber. Okay. So, at a high intensity the absorption is 0 and the transmission is highest. So, once it is transmitted here, this mirror will reflect it back and it will go back. Perhaps all these molecules have stayed up there and this will just go back and go back to this thing. And by the time it comes back, many of these molecules will have fallen back to this level, and again you will have to bleach it. You bleach it and then it just shuts off. And this process goes on. So, what one has to do is, these molecules from this level should also relax back at a rate faster than the light can go through and take a round trip and come. Okay. So, when again the round trip comes, again it is shut, and then a higher intensity part comes in and it goes through. So, that cycle should go on. That means you have a bleaching process and you have a relaxation process. You have a bleaching process and you have a relaxation process. So, open and shut, saturable absorber without any external electric field or any external trigger. It is happening on its own. So, most often you can think of it this way, think of it in this kind of a way, that in the resonator within the active medium you have these kind of light pulses, small spikes and all that, and so a big spike comes in and small intensities which are growing inside that. Okay. And these come and hit the saturable absorber. When these small intensities come and hit the saturable absorber, this is what happens. Okay. When these small intensities will hit the saturable absorber, this sort of a thing will happen, it will bleach it. Okay. All these small intensities are not allowed to pass through. But when you have a large intensity like that, the small intensities have already done the job of bleaching, and the large intensity just passes through, and then reflecting back it goes in. And this grows, it is going into this medium and it is growing. Okay. And so that means these small intensities are getting suppressed at each round trip, because they are helping to shut this down, and then again it is transparent to this thing, and then it transparent to this big spike, and it goes on, and only this grows. So here you have one pulse at the end of it. Once it has grown, you will get one pulse here. Now in the next round trip, again there may have been something similar, and you will get another pulse coming through, and so it will go on. Okay. So that is the job of the saturable absorber. So in semiconductor it is generally called SESAM. M stands for the mirror. So by very good technology nowadays, you can stick this saturable absorber to the mirror. So you will have a resonator like this, and this mirror itself is a saturable absorber mirror. So that means this acts as a mirror and a saturable absorber. So this reflectivity is very high for very high intensities, okay, when I is large, and this reflectivity is low when I is low. When the reflectivity is low, that means it corresponds to these kind of small spikes. There is no reflectivity for this, but for a big spike there is a big reflectivity. Basically the saturable absorber and the mirror have been combined together. With very good technology nowadays, that is possible, where they grow layers and layers of semiconductor in such a way, so you get a good reflectivity over there. Now the thing is, you can also look at this saturable absorber part. Instead of this, you can also look at it in another way, that suppose I have within my cavity here, I have a big pulse that has grown, a large intensity pulse. Okay. It has grown inside this cavity here. Now here is my saturable absorber, SA. So when this part of the, this is time and this is my intensity. Okay. Now when this part of the pulse comes in, this part, at this time the intensity is low, you can see it is somewhere here. At that time it bleaches the saturable absorber. At low intensity, instead of having difference by, you can have in the same pulse this lower part of the saturable absorber is here, okay, and it bleaches it. So once it bleaches it, this part of the pulse just passes through. The saturable absorber is transparent to it. Okay. So that's what this initial part of the pulse does. And because it has done this, you can see in time the pulse has become a bit short, it's become a bit narrow. This part is disappeared, only this part has come and grown. So it's become a bit narrow, and in each round trip it becomes a bit more narrow, becomes a bit more narrow. That's how also one way of looking at it is another way in which the pulses grow shorter. Of course, you get the shortest pulse with the one which has the maximum gain bandwidth of or delta nu g. In practical things, the most popular laser for very short pulses is a tie sapphire laser. Which has a very, very large gain bandwidth. So, obviously, a shorter pulse is possible from a tie sapphire laser. Okay, let me give you that table, which I'll go back to the previous slide. See here. These are some mode lock lasers. So, in case of I've given ruby lasers and delta nu, okay, that's the bandwidth, the number of modes locked or the bandwidth or the gain medium bandwidth, whichever way you look at it. Delta nu is 10 gigahertz. So, obviously, delta t is delta nu inverse, that gives you 0.1 nanosecond, and this is by calculation from here, but the actual observed pulse width is also around somewhere around 10 nanosecond, may not be, this is the limit to which it can go. Suppose I have a 2 gigahertz, which is smaller than the ruby, ND YAG is much smaller bandwidth, delta nu is much smaller. So, you get a 0.5 nanosecond pulse as compared to 0.1 nanosecond. ND glass in comparison with ND YAG, both of them have the same wavelength of lasing, but ND glass has a larger bandwidth, 200 gigahertz as compared to 2. So, obviously, the pulse delta t, the pulse width of the pulse that is coming out is 5 picoseconds. So, in some mode locked lasers you do get picosecond pulses. Okay, it is possible with ND glass, and some observed pulse width means some practical lasing action that they have seen, it is around 50 picoseconds, very close to this. So, this is a very good estimate. Take the inverse of delta nu, you get a good estimate of the output pulse that you will get. In case of dye, which has dyes are also used as an active medium, not only in saturable absorbers, but also as an active medium, dye lasers, and they are good for obtaining short pulses because they have such a large bandwidth, 400 terahertz, 44 terahertz. So, this will give you a femtosecond pulse of 22.7 femtoseconds, and the observed pulse is 10 femtoseconds. This gives a larger value here, but they have observed much smaller. Nowadays, the most popular in the 800 nanometer range, dyes can be 700 nanometer or even tuned, you can tune it, as I have said before. Titanium sapphire is very popular because again in case of the dye you do get very short pulses, it is a sort of a messy affair. It has you have to dissolve the dye and sometimes there is leak and all those kind of problems are there. Unless you are particular about which wavelength you want, one will go and if you are particular about just how short is the pulse, everybody goes in for tie sapphire, which is a crystal and it is clean, and it will be around in the 800 nanometer to 1 micrometer range. And again you get a pretty good bandwidth, bigger than the dye, 128 terahertz. So, that means 7.8 femtoseconds, and in actual experimental value they have got as 90 femtoseconds. So, this gives you a good comparison of how short the pulse can go when you have mode locked pulses. Okay. So, if I go back again to the here, okay. So, tie sapphire is the most popular oscillator used nowadays, but then again ND glass is also a very popular material for getting ultra short pulses, because you get a larger energy you can extract from ND glass than from titanium sapphire. And so from a titanium sapphire laser you will get a train of pulses, which is in the you get a whole train of pulses from the oscillator, this sapphire oscillator. And this is in the somewhere in the 90 to 100 megahertz scale. So this occur in that is a rep rate, repetition rate. And each pulse will be somewhere around in the femtosecond range, as you have seen, and you will get an energy in millijoules each pulse. So it has a rep rate of this thing. In case of ND glass, you will get a rep rate of around say 150 say megahertz. It will range between 108 to 150 megahertz. Okay, and you get a larger, much more than a millijoule. So this is how. So again, in this case also you get this train of pulses, and this also a train of pulses. So you can imagine the large intensities. Remember large peak powers, E by T. Your T has gone into the femtosecond range, and your energy you have in millijoule or microjoule level, and so you get very high peak powers. Okay. So basically I have described the synchronization of all these modes which overlap with each other at a time interval of T is equal to 2D by C, and they are the phase wise they are well synchronized, and that is how you get this mode locked pulses. So now the point is, when I have such high peak powers and such high intensities, I go into the into nonlinear optics. No longer is your optical system linear. At high intensities, at these pulses, they will create all havoc inside a medium. Okay. They will just create havoc inside that medium. Now I want to tell you what this nonlinear optics means. We know what is plane optics. If you have a glass slab, you have an input ray, it will bend, some part of it will bend and some of it will be reflect back, glass will go in. Most of the time there is, it is dependent also on the frequency, because you have a prism, and then in a prism you get a whole lot of wavelengths which are moving out. Okay. So this is what is linear optics. That means your refractive index is behaving linearly. It does not really change much with the intensity of the light that is falling. Okay. So, but what happens in nonlinear optics? You have such high intensities, the whole the medium just behaves differently. It just goes out of control, I should say, and that is what you want to control. And it gives you some fabulous results, when you have these nonlinear phenomena taking place in optics. Okay. So, this will be my topic for my next lecture.